Hello everybody, this is Program 123 again. Today we're gonna be solving this problem that is named Goldbach's conjecture. It's 543 of Yuva Online Judge. To explain this concept of Sieve of eratostenes of the CP algorithms webpage, basically this problem says that we have to prove the Goldbach conjecture up until this number, that is 1 million. Okay, it says that every even number greater or equal to 4 can be expressed as the sum of two prime numbers. So they're gonna give us some test cases, and each test case is gonna be one number n, which is gonna be between 6 and 1 million. So the first step to try this Goldbach conjecture is to know how many prime numbers are there between 6 and 1 million. Okay, so we're just gonna Google it quickly. We have no more than 78,498. We needed to know how many prime numbers are there between 6 and 1 million for us to know which time complexity will be okay with our problem. So with this, we can see that it is clearly not a quadratic algorithm that we gotta code. Okay, so as you can see, we're gonna have value of n between 6 and 1 million, and we have the example 8 is formed by 3 plus 5, and 20 is gonna be formed by 3 plus 17, and they are asking us for that pair of prime odd numbers that the difference b minus a is maximized. That's why they are taking 3 plus 17 instead of 15 plus 5, for example. So we want this to be maximized. In other words, they are asking us for the greatest b and the lowest a. So as I told you before, we need to first find the prime numbers up to 1 million. So first, how are we going to generate all these prime numbers? Well, first of all, let's declare this constant that is gonna be 1,000,005, and we're going to declare a bit set of that size. The idea here is simulate the work of eratostenes in order to find the first prime numbers. You maybe saw that in high school or in elementary school. The idea here is first we're gonna say that all the numbers from 0 to 1,000,004 are primes. Then we say 0 and 1 are not. We are gonna start from 2 that we know that is prime. We're gonna mark all the multiples of 2 as not primes. Okay, so first we ask, is this variable I a prime number? If it is, well, I'm going to mark all its multiples as not primes. Why do we start in I times I? Well, I don't have to consider I times 1. So for number 2, I have to consider I times 2, I times 3, I times 4, and so on. But did you hear that? I consider 2 times 3. So when I is equal to 3, I don't have to consider it again because it would be redundant, and have to consider it again because I have already considered it. So I don't have to start from I times 2. I have to start from I times I because all the previous numbers are already marked as not primes. Okay, so with that in mind, we just mark all those multiples as not prime. Then this line doesn't do anything at all here. Okay, but since we know that we're going to have up to 78,000, we're gonna reserve 79,000. So since the problem is asking us for odd prime numbers, our list of prime numbers is gonna be 3, 2, 1,000,005. Okay, so if this number that I am currently looking at is prime, I'm gonna add this to the list, and I'm gonna increase the value of this variable c. That is the one that is gonna tell me how many prime numbers are there. So for us to know how many are there exactly, we're gonna print it at the beginning, and we're gonna see how it turns out. So you see we have 78,498 prime numbers. Okay, so we don't need this line anymore. Let's erase it. Now this is how we generate the list of prime numbers up to 1 million. If you want to do it up to 10 to the power of 9, I wouldn't recommend that, you guys, because you're gonna have memory limit exceeded. You're gonna need 1 gigabyte of memory. So to solve the problem, what are we going to do? Well, this is one of those problems that in which the test cases are terminated by a number 0 in the input. Okay, we're gonna write an infinite loop, and we are going to declare an escape sequence right here. Now I don't even need this variable band. I declare these two variables that are gonna be the numbers, the prime numbers that add up to n. Originally I declared them as 0. I set them to 0 because I wanted to see where my bug when coding was, so I declared them to 0. Now I don't even need band here, not here either. And well, so what are we going to do? We are going to start from the first prime number, and we are going to try to find a partner. Okay, so we do a binary search over this vector of numbers, of prime numbers, in which we are going to look for n minus the prime number that we are considering, and we subtract num that begin to get an integer value. If I don't do it, I'm gonna get a pointer, an hexadecimal address, and I don't need that. I need an integer. Okay, so we do binary search to find the partner, and then we ask, do these two numbers add up to n? If that's true, we're gonna finish that cycle, and we just have remaining printing these numbers, n equal to num1 plus num2. And for those of you who want to know when to use Sieve of eratostenes, let me tell you that we use it when we have to constantly know whether a number is prime or not. We do it either by binary search on the vector of primes or in constant time over the bit set. Actually, I don't need this condition either. Okay, so we run this code again, and we're gonna see the answer that it gives us. Okay, so we get 3 plus 5, 3 plus 17, 5 plus 37. And that's it, you guys. So I hope you enjoyed this video, and this video was useful for you as well. Thank you so much for watching. Don't forget to share this with those who need it. Remember, stay home programming, and bye bye.